let's start with our algorithm, which name is next smaller jumping. So let's start with the problem. So problem says that it's very easy, and you already solved it before. So problem says that given an array A, for each index I, find the next I, which is the first index to the right of I, that is smaller than AI. Okay, a very classical, typical problem. So let's come with some example too. The example is our array is 5, 8, 2, 6, 7, 9, 1, 2, and then you can see arrows that shows the next element of every element. Like next of 2 is, for example, 1, next of 6 is 1, or for example, next of 5 is 2, and that is array next, which contains the index of the next smaller element. So what you may be always doing for this problem was a stack, right? Monotonic stack. Yeah, you always did it using monotonic stacks, right? So anybody thinking about any other approaches before? Like anybody thought that this problem might have some other way to solve? This is a very classical, like typical problem, like maybe as easy as partial sum, right? Maybe as typical as partial sum. So we don't think that partial sum has other way to do. And same goes with this. Like we don't think that this simple problem, this typical common problem, has other solutions. And maybe easier to implement, maybe with better runtime, not time complexity, as it can be less than ON, which stack is, right? So anybody thought about this problem before, but without monotonic stack? Binary search plus sparse table. But what I want is easier to implement, less runtime. So let's start with something that somebody who for the first time sees the problem will implement. So what he will implement is going backward in the array, setting next to the next element, and having a while to go find the first next element. That's it, right? This is something that like every newbie on Codefoces can do and will do if his first time to see this problem, right? What is the time complexity? N squared. So reduce this problem. Like now I want to make some challenge of like, do you remember like elementary schools challenge we had, like change one line to do blah blah, change one operator to get result of 21, like something like this, some magics like this, or maybe change position of 1 in this equation to make it work, something like that. So we want to change one line, just one line, and just a few characters. If I remember correctly, it was like 10 to 15, something like that. Change a very few characters, like just one line, to reduce it to ON. So that is our challenge now. We have this code. We can have just one line change, and we want to get ON. Please tell it louder.
If I'm searching for the next smaller element, and we are on 10, so the next of element is 10. So we don't bother about 11, 12, or 13. We bother about the 9 or 8. It would be in the right. So that would have been stored by being next of I. That's what we can. Instead of going to I plus that, we can just jump onto the index delta next of I.
Okay, so instead of doing plus next I, let's do next I. Let's set it to next of I. Nice idea. But how much time it can reduce? Like, what is the time complexity of this algorithm now? Now this code has linear time, so it's ON. So it's just changing one line. We reduced it to ON. And so why does it work? There are many ways to say why does it work, but let me come with one proof that why time complexity is good. The reason is, let's say element I is skipping element J if sometime next of I was J, and then it was discovered that J is more than I. So it skipped it and went to the next of J. What I argue is this jumping happens for every J at most once. So if I can prove it, that's it, right? Because there are n elements, each of them has at most one jump, and we have total of O(n) jumps, and this time complexity for this code is just calculated by jumps, that's it, right? So almost always amortized analysis do like this, right? Because if I try to calculate time complexity from, like, let's say for each I, how many jumps can I have? O(n), right? If I do analysis like this, I'll lead to O(n) squared. But I need to count the number of operations from a different way. Like if I do straightforward like this, I'll lead to O(n) squared. But if I'm smarter and use this as, let's say, let's count the number of jumps happen on every J, then I'll find that it's O(n). Let's say Y. Consider that I have two elements, let's say I1 and I2, which jump over J. Like this one jumps and this one also jumps. Like this goes to this and this one also comes to this and then jumps. This is a contradiction. Why? First of all, what I have is A of I2 was less than A of J as it jumped over it. Otherwise, if this was less than this, that was it. So first of all, this happens. Then consider the case that so let's have some equation for these two. So if AI1 was greater than AI2, I would reach I2 before I reach AJ, because I'm going to next. I won't miss any smaller element in my path. Otherwise, so we can say that AI1 is less than this one. So now what we have is this. So AI1 is less than AI2 and it's less than AJ. Then what happens is before I reach AJ, before I reach J, I already when I was doing like next, I first reached I2 and already jumped over J, and I can't jump on J. So I will find this thing before this, because this is less than this. AI2 is less than AJ, and I will find this before I find AJ, and I will directly jump over it. So that's why this works in O(n). So here you can see steps of this algorithm over a somehow large array. Like as you see, it goes to next and goes to next. Like for one, it was very good example. So look at what happens for 1. Goes to 8, then 5, then 4, and then jumps to the end. Okay? Finally, let's compare this NSJ with the old method monotonic stack. As you can see, one line less than that, and also it has 94 characters. This one has more than 100 characters. And you know, both of them are easy, like they are very easy to implement, both of them. But first of all, I'm almost sure that you had some difficulties sometime implementing this, for maybe forgetting about pushing to a stack and all. You forget about, at least I remember more than 3 times I did this, like forget to push into a stack and see why the result is just gibberish. And that one works, like your mind completely understands it, like I'm going to the next of next, that's it. So it's very like optimized naive code instead of something that you really need to learn. Like a stack thing is something you really go learn it, but this is something you can invent on your own. Like actually this story was, I told some children this problem. Children, I don't mean very little, like real children, a kid, this problem. I told him, and he was like, didn't know the solution before. And what he invented was that algorithm. And for me, it was like, for sure, it's wrong. Let me come with some contradiction, counter tests, like hack tests. And I tried first increasing, then decreasing, then increasing, decreasing, and so on. And it was like, it's working. And after like 5-10 minutes, we were just walking. So I didn't have some papers to test in like numbers. And yeah, it was like working. So I started to prove it. Like it's what we always do, right? We first try to come with some counter tests when we don't believe in some algorithm, when we don't believe in some way. And when we see that, yeah, it's working on all of the counter tests, we try it, but we didn't try to prove it. I tried to prove it, and yeah, it was proved. So I understood that this is correct. What makes this NSJ interesting for me is I never see anyone who knows this or implemented this during a contest, for example. Like I went checked a lot of like top people in Codefoces standings for problems popular for this problem. Like this problem appears a lot, right? This is something that you maybe solved 20 times before, right? So I had some problems with this tag, and I went over them, like sorted by solution size to maybe find something like this, or starting to search the standings of contests to maybe some legendary grandmasters and all implemented this, and no one implemented like this. Everyone implemented like monotonic stack. So it was a sign that following people who are being said greater than us always doesn't lead to the best solution, even for very easy problems. Like this is a very, very easy problem. So every single problem, even that easy as this, is open for improvement, is open for coming at least with a nicer implementation. So that's what I recommend to you. Like when you learn a new topic, don't try to read code from others. Try to invent something new, some short code, some very neat implementation for yourself. Almost always what you do is not better than what others did before, because you know the probability of being a random number more than like n random numbers is very low, right? But it's still there is a probability, it's not zero. So for example, I remember first time I learned heavy light decomposition, I started to implement it on my own, and it was like 300 lines of code, while you know the good implementation for that is maybe just 100. But yeah, there is a lot of learning happens when you do this, trying to improve, maybe even trying to improve others' code. Like you read code from someone who is great, and you still try to improve his implementation. It comes with a lot of learning. Thanks for watching. If you found this video useful, please like, subscribe, and ring that bell. By the way, YouTube thinks the video down here is just perfect for you. Give it a watch and let me know in the comments.